This is video capture of a lecture sitting alone in my office for the RSA section of the pre-reading for CS 4050, and I'm going to talk about pages 30 through 31 in this little video. I'm going to try to keep the videos modular so they'll be easier to work with. I'm using the software Explain Everything. As far as I can tell, there's no way to go back and edit the videos, so it's just whatever blithering I end up doing. So the reason we're doing the RSA at this point, after studying divide and conquer, is that the exponential multiplication, so this is the problem of taking a huge integer and raising it to another huge integer in z sub n. It's called modular exponentiation, and we're going to learn to do that very efficiently with divide and conquer. If this without the divide and conquer algorithm, this step would be hopelessly, absurdly impossible. Okay, so also there's probably other parts of this work that use divide and conquer along with other algorithmic ideas, including just to multiply a times a. That's going to take, if we implemented it efficiently, we could use Karatsuba's algorithm. Yay. Okay, so the overview of RSA, you may have heard some of this in other classes, like a security class, but don't worry, what we're going to do here is going to be extremely technical and mathematical, your favorite things. So, somewhere we have headquarters, and in headquarters, the sneaky people there they come up with two prime numbers, and they compute n is equal to p times q. And they come up with an even more weird number called e, and then they just put out on their website, they completely publicly publish, make known to everyone in the world those two numbers. So anyone in the world can take a message A that they want to send. So this is just anyone wants to send A. What they do is they compute A to the E in z sub n, and we'll call that C. Let me, just for fun, because we can do it, rub that out. Okay. So those people then send the number C happily off to headquarters. But of course, bad people can listen on the internet, and so a bad person can intercept that. But if they can't factor in and come up with the prime numbers to repeat what headquarters is doing, they simply can't read. They can't decrypt C. Back at headquarters, they have, if they know, knowing P and Q will C allows them to compute the magic number D. So back in headquarters, they compute, oh, this would be a great place to do this enlarging. Back in headquarters, they compute C to the D in z sub n, and that's equal to A. Yay. Okay. Back into more or less where we were before. That's the problem with this zooming. Okay, so that's the introduction to the RSA, and we're going to now go on and look at the tools one at a time. So I'm going to start a new page, I hope. So now, apparently the recording is continuing, so now we're going to look at z sub n and make sure everyone knows what that looks like. Okay, So z sub n, for example, z, whoops, what the heck? Somehow lost the pencil. So let's just look at z sub 13. So this is integers mod 13, they call it. And this just means ordinary integers. And you do arithmetic. We've done this before when we were doing the FFT stuff. Do arithmetic as usual, but then we bring in n equals 0. So n equals 0, it makes everything different. So for example, 6 times 9, nz sub 13. We'll always say nz sub 13, if that's what we mean. So 6 times 9, you just do the arithmetic normally, and you get 54. But 54 is in fact equal to 2. Why? I'm getting very pedantic and condescending here. Well, the multiples of 13 are 13, 26. Of course, there's also minus 13, minus 26, but usually the positive ones are easier. 39, so I'm just adding 13 each time, hopefully successfully. 52, 65, 78, 91, 104. Anyway, all right, I'll finish 117 and 130. By finish, I mean go out to 10 times 13. Okay, so to figure out what 54 is, you just look over here and realize the closest number below there is 52. So the all of these, of course, all of these multiples of 13 are 0. So in this kind of clock arithmetic of Z13, every time you hit 13, you just throw it away. Okay, so that's a little bit harder though. What if we wanted to do, say, 200? What if we got an answer of 200 and we want to know what it was equal to in mod 13? Well, if we don't want to make a long list of all the multiples, which obviously is hopelessly inefficient, what we do is whip out our calculator and take 200 divided by 13, and what does that equal? Well, let me see. Turning to my calculator, which happens to be here, I will take, if I can find the keyboard. You can't see this because it's not part of the exam explain everything world. So 200 divided by 13 comes out to be, on my calculator screen, it says 15.3846, blah, blah, blah. Okay, so what is that? That means that when you divide 200 in the old school days, grade school, elementary school, you divide 200 by 13, it goes in 15 times. And then, if you finished off, I don't know what 15 times 13 is, but whatever it is, somewhere down here I'd get the remainder. But the remainder is just 0.3846, blah, blah, blah. But what is that? That's the real remainder in the calculator divided by 13. So what we need to do is get a hold of this number and multiply it by 13 to get our real remainder as an integer. So all you have to do is say 200 divided by 13 equals 15 point blah, 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 and then say minus, and then you have to read the 15, which can be a pain for big numbers, minus 15 equals, that'll expose the remainder all by itself, and then I say times, it's the calculator times key, times 13 equals, and what shows up? Well, let me do it. So I say minus 15 equals, so I just get the remainder all by itself, and then I say times 13, and I get 4, oops, had the pencil upside down, 4.999999999, which obviously, if it were for rounding error, would be 5. Okay, so that gets us up to about the end of page 30, except to point out that in Java, we'll be doing hand calculations like on the test. We're using a calculator, but in real life, if you actually want to implement RSA, you could use the Java big integer class or the equivalent thing in whatever programming language you're using, you hope. So the big integer class has multiply and divide and all these things. And it also has the remainder, the mod operator. Okay, so let's go to another page and continue. Okay, so I'm also looking at the pages. So we're now on page 31. Okay, so it turns out, this is a huge thing for everything we're going to do, that a to the k is interesting in z sub n. So what do I mean by that? Well, let's just do one tiny example. So let's take z sub 13. So in z sub 13, let's take a equal to 3. So the powers of a are 3. So we got 3 to the 1 is 3. 3 to the 2 is 9. So these numbers are less than 13, so we don't have to reduce them. 3 to the third is equal to 27. What? But that is equal to 1. Okay, so that was exciting. But if we keep going, then it starts repeating, right? 3 to the fourth is 3, 3 to the fifth is 9, 3 to the sixth is 1. It's 27. When we reduce it, it's 1. Okay, so this is interesting. 3 was kind of a not that good of a number for this purpose. So as it turns out that, but it is true that if we go up to 12, obviously 3 to the 12th will equal 1. So number theorists way back discovered this amazing property that a to the n minus 1 is equal to 1. Sorry, a to the n, n minus 1 in z sub n. So that's a fact, and we're going to prove that later. But first, we want you to explore that. So you should now do embedded exercise 22, and this is where the recorded video lecture is far superior to the live one, because if you're wise, you really will stop right now and work this out for yourself. And when you start up the video again, I'll do it, but you should do it for yourself. So try a few A's, and in particular, make sure you use like a equals 7, say. That maybe you can just do a equals 7. That's the one I'll do when we come back, okay? So seriously, whenever we hit these embedded exercises, you need to at least take a shot at doing it, because if you can't do them, you may not be following what we're talking about, and you need to replay the video. All right, so I'll see you in a few minutes. Okay, so let's start a new page with my answer for EECS 22. So, and all we're doing here is explore the powers of 7 in z sub 13. So I'm just going to list them out and do the work in my head. So 7 is the 7 to the 1, and then we multiply by 7. If you didn't figure that out, I once did a junior class with high school students, and I asked them to do this, and they used their x to the y key on the calculator, which is a terrible mistake. They every time they wanted to have 7 to the 5, they would do 7 to the 5, get some big integer, and then laboriously reduce it mod 13. And that's just silly, because look what we can do. 7 times 7 is 49, which immediately becomes, what? Is equal to, let's see, I don't have my multiples here. So it's 10, right? Because there's 33 times, 3 times 13 is 39. So this, throw away those 39, and you get 10. And the next power then is 70, but that's equal to 5. because 65 is a multiple of 13. And of course I could use the calculator trick on any of these if they got too irritating, and we'll have to later. Okay, and then 5 times 7 is 35, right? Which is in fact equal to, let's see, 26, 39. So it's actually equal to 9, because the 26 plus 9 is equal to 35. So it's 9. And the next power is 63, which is, and I have to be honest with you, I remember 65 is a multiple of 13. So what I'm actually doing here is thinking, oh, this is minus 2. And minus 2 is equal to what you add to 2 to get 0, which makes 11, because 11 plus 2 is 13, which is 0. It's a weird world, z sub 13. Okay, so, oops, I'm going to erase that because I can. Okay, so let's see, so where were we? So if we make a more organized chart, we're doing 7, 10, 5, 9, 11. Those are the powers. That's 7 to the, 7 to the 1, 2, 3, 4, 5. 7 to the k, where k is it? All right, that's stupid. Sorry, I'm obsessed with this. I'm gonna make a bigger eraser. Still not very big. I must be doing something wrong. So if k, oops, pencil works better for writing. So k equals 1, 2, 3, 4. Wait, 1, 2, 3, 4. You're gonna get tired of seeing me erase things, but I love it. 5, 6, 7, 8, 9, 10, 11, 12. And down here we have 7 to the k equals. Okay, so carrying on. So the next one is 77, which is actually 12, because 78 is a multiple of 13, I believe. I should be sure about that. It's also, you can also look at 65 plus 12 is 70. Okay, so this is 12. And the next one, so, 12 times 7 is 84, I believe, which is 6. I made that too small, but guess what? We can zoom in. Okay, and right, because it's 78 plus 6. You're probably getting sick of me doing this arithmetic. Okay, and then 7 times that is 42, which is equal to 3, because it's 39 plus 3. And then 7 times that is 21, which is what, 13 plus 8. And 7 times that is 56, which is 52 plus 4. And 7 times that is 28, which is 26 plus 2. And 7 times that is 14, which is equal to 1. Ta-da! Okay, so this is an interesting case. In fact, if the number a doesn't divide, oops, if the number a doesn't divide n minus 1, with no remainder, we're going to show later that you always get no repeats, no early 1. So it's always true that a to the n minus 1 is equal to 1 in z sub n. But the question is, it's nice and very incredibly common if no earlier a to the k equals 1. So we'll come up with that later. Okay, so that concludes the work with embedded exercise 22. And this randomness that we see here, like, it's pretty unpredictable how these different numbers, here I'll show off here, I'm going to use an arrow if I can. See these numbers here, those numbers are in fact kind of random looking. It'd be pretty hard ahead of time have predicted what those were going to come out to be. So actually, this modular arithmetic is also used for pseudo-random number generators. Okay, so that's a good stopping point for this entire video. And I'm going to break the videos into small chunks because, for one thing, I think YouTube is limiting my account to 15 minutes tops per video. Plus, it's just easier to deal with smaller pieces. So next we'll go on to look at modular exponentiation.